with in Cambridge. So today I will talk about non-Markovian dynamics. Yeah, is that better? I think that should work.
No, it works.
Yeah. Okay. So I will be talking about non-Markovian dynamics in many-body systems, and main question I'll be asking, what is the computational complexity of non-Markovian dynamics? And this would bring us to this notion of temporal entanglement, which I will define, and from there we will both introduce some new efficient classical methods based on tensor networks and give some guarantees on their performance. And also then I will turn it around and ask how can we emulate essentially a many-body path using dissipative evolution of just a few qubits. And then I will talk about experiment that we did at Google in that direction. So first part will be more theoretical, and then we'll get to the experiment. So of course, there has been really a lot of remarkable progress in quantum simulators, synthetic systems such as ultra-cold atoms, right, which are extremely tunable and very much unlike conventional materials in that there is no phonons, no heat bath, and also the systems have long time scales, right? And that really sort of boosted interest in non-equilibrium dynamics of isolated many-body systems, right? Because in these systems you can do experiments such as quantum quenches, right? You can shake them and characterize the subsequent evolution in a controlled manner. So in a way, these systems are a lot simpler than driven materials that, for example, Andrea talked about this morning. Right, so this really boosted interest in non-equilibrium phenomena. There are many platforms ranging from cold atoms to superconducting quantum processors and Rydberg atoms. And what also another sort of facet of non-equilibrium phenomena is that their computational complexity. So in general, if we are, for example, looking at a quantum quench, so we have an interacting system of spins, right, and we started off in some relatively simple, even classical non-entangled state, product state, and then as the degrees of freedom interact, information spreads, right? Generally, you expect that there is some velocity, finite velocity of information spreading, and there is a lot of entanglement generated between different degrees of freedom. So for example, if I have a one-dimensional system, entanglement would generally grow linearly with time. And turns out that exactly takes you to the corner, to the major part of the Hilbert space where we don't have good classical methods to approximate such states, right? So methods that we have, notably based on tensor networks, work when entanglement is relatively low, right? They're actually based on that, and then we can get efficient classical approximation using this tensor network diagrams, right? And therefore, you expect that many of the problems of non-equilibrium dynamics would be also computationally hard. And therefore, on the one hand, right, this poses a challenge for theory to find corners and cases where we can either have some form of solvability or still have efficient description despite the fact that wave function becomes very entangled, right? And naturally, that's been one of the main targets for quantum processors, right? Looking for useful quantum advantage. Now, there is, of course, another big field which is very well represented in this workshop, related to this idea of controlling correlated materials by bringing them out of equilibrium. And right, so as we heard already this morning, so you can drive phase transitions, right? You can try to control superconductivity theoretically, these are, right, if you especially try to describe this microscopically, these are extremely hard problems, right? Even much harder than quantum quench, as I previously mentioned, because here you have to deal with this ultra-fast dynamics of coupled electrons and phonons. And I will not attempt to say anything about this, right, because this is very hard, but I will say something about an ingredient of family of methods which are used to model, right, model correlated materials, which are embedding methods such as dynamical mean field theory. And in this method, really the central ingredient, central bottleneck are quantum impurity problems, right, which are self-consistent. So essentially, you try to model your material as an impurity embedded in a non-interacting environment, and its properties are self-consistently tuned to emulate a given correlated material. And so I will get to that later on. So now, let me give you right away the main starting point for what will follow, how we started thinking about this. Indeed, there is this idea that complexity is related to spatial entanglement, right? And things which are entangled are generally hard. But what we can do, so rather than thinking about the many-body wave function and its evolution, right, we can instead take more of an open quantum system point of view. So let us, for example, I have my many-body system, but often what I care about are local observables, right? And for example, so let me focus on some subsystem, let's say one spin or a few spins, and think about the evolution of this subsystem. And I will treat the rest as an environment, right? I will treat the rest of my many-body system as a complicated environment. And then, so this gives us a different view on this problem. So instead of thinking about full wave function, we describe the effect of the buff. And that's encoded in the influence functional due to Feynman and Berman, which is essentially this is a functional on the space of trajectories, time trajectories of your subsystem. And I will explain a little bit more what it is. And just changing this, your view from spatial to temporal, if you wish, actually gives you quite a bit of mileage. So we will see that there are some exact solutions, and then this gives us another set of phenomena where we can have efficient description based on temporal entanglement and low temporal correlations as opposed to spatial. And in general, I think it just gives you quite a complementary and fruitful perspective on really a variety of many-body phenomena, many-body dynamical phenomena. So with that, so let me just first focus on this Hahn equilibrium dynamics and just remind you some of the concepts that community has been studying for some years now. Right, so if we are thinking about many-body system pushed strongly out of equilibrium, by far, the most common dynamical regime would be thermalization, right? So your system finds thermal equilibrium. There is an exchange of energy between different degrees of freedom. This is related to the notion of organicity, and this tells you that your system can act as a good thermal bath, good quantum thermal bath. And at the level of quantum many-body eigenstates, the way to understand it is via eigenstate thermalization hypothesis, which essentially tells you that individual eigenstates of the system already look like thermal ensembles. So if you take an eigenstate of such a system, which is a good bath, every small subsystem would essentially have a thermal density matrix. And this also means that thermal eigenstates are highly entangled, right? So that's another piece of information why entanglement is generated quickly as you thermalize. Thermalization also means that quantum information gets scrambled, right? Your state really cares only about global conservation laws, and that triggered a lot of interest in finding cases when you can avoid thermalization or slow it down. And there are a few very different possibilities. Of course, there is one very sort of classic way to not to thermalize, which is integrability. So, for example, if you have particles which are non-interacting, right, each particle occupation number is integral of motion, the system doesn't thermalize. Or if you have certain spin chains which are very symmetric, right, which are beta and that's integrable, do not thermalize. Integrability is pretty fragile, right? Phenomena which are much less fragile and driven by disorder is many-body localization, right, where disorder makes the spectrum locally discrete, and that prevents exchange of energy and thermalization. So this is strongly disordered systems are generally bad path, and this has to do with the emergence of local conservation laws which are sort of adapted to disorder. Now there are also other interesting scenarios such as quantum many-body scars and pre-thermalization, which a very general sort of mechanism to make thermalization, not to avoid thermalization, but make it extremely slow. Right, but those are broadly the possibilities that have been explored and are being explored still for high equilibrium dynamics. And with that, so let's jump into this analogy with open many-body systems. And the starting point really is this classic formalism by Feynman and Ternan, right, who were interested in describing a small quantum system, let's say a spin described by coordinate q of t, coupled to a bath, and they modeled the bath as a bunch of non-interacting oscillators, right? And those I will denote by q capital. And you can write a path integral, right? So you're interested in probabilities, so you will have two copies, right? You have forward and backward amplitudes in the Keldysh language, if that's what you're used to. And then what you can imagine is integrating out bath degrees of freedom. And this gives you this object, which looks scary, but ultimately this is the weight for a given trajectory of your system that you get, right, once you've summed over bath degrees of freedom, right? So it's a non-local functional of the your system trajectories, right? And that's the Feynman-Ternan influence function. And this is object that you need if you want to describe a bath. In case of bath of oscillators, it's very convenient because you can, Gaussian integrals you can compute explicitly, and right, you have a starting point, and then you can start playing with dynamics of your spin coupled to a bath of oscillators, and this is exactly the subject of this also classic work by Tony Leggett and collaborators. And this problem of spin coupled to a bath of bosons is extremely rich, of course. So this Riemann field is still quite relevant and quite hard, I would say, to get through. But today we will do something different. So we will try to do this, but for a many-body bath, right? So system itself would be a bath. And just to give you a tiny bit of intuition about influence functionals, if you haven't encountered them, especially if you have what I would say would be completely obvious. So let us consider the simplest type of influence functional when you have a spin, right? Spin, and you have to worry about two trajectories, forward and backward trajectory, right? Sigma and sigma bar, I would call them. And let's say your spin is interacting with a classical noise, right? So there is just a field, fluctuating field along z direction with some correlator, right, some kernel f, then you can do averaging over such noise immediately, and what you find is that your influence functional is just a Gaussian functional, which effectively what it does, it gives you weight which is smaller than 1 for trajectories where forward and backward configurations are not the same. So effectively, it kills quantum interference effects. Right? There is also an analogy with weak localization. Right? That's exactly, it does not affect trajectories where sigma is equal to sigma bar, because those are classical contributions, right? But the quantum interference becomes gradually suppressed, and that's one piece of intuition about these influence functions. So they tend to suppress quantum interference effects. And now, so going to the many-body systems, so what is quite convenient is to think in terms of tensor network description. So I can let me start with the sort of simplest possible model of quantum many-body dynamics, which is discrete, right? Discrete dynamics of a spin chain. So I have a one-dimensional, in this case, spin chain, spin 1/2, and then I denote Pauli operators as z, x, and y, right? And this is nothing but a discretized transverse field Ising model. So I'm applying x field with amplitude g, h field, z field with amplitude h, and then Ising interaction with amplitude j. There are 3 parameters in this model, and I can I can draw the evolution of a density matrix of the spin chain as this colorful tensor diagram, right, where each tensor gives you the corresponding amplitude, and you sum over intermediate states. So that's nothing but a discrete class integral, similar to what I was writing when I defined influence function. And typically in tensor network methods, you try to take advantage of low entanglement of the spatial wave function, right, and approximate the state with tensor networks. But let's do something different. So let us instead trace out, right, in the spirit of analogy with open quantum systems. So let me focus on the dynamics of this spin and trace out everything else. So I could do it in different ways, but the outcome would be that I would end up, this part here will give me exactly a tensor which would be the influence function, acting on the space of trajectories. And now to finding it, so one way to find this functional is essentially to take one slice of the tensor network, right? This blue slice, that's the transfer matrix, and essentially act with it over and over again. And what you would find that this would give you exactly the influence function. So influence functional is the leading eigenvector of the dual transfer matrix. But now what is most important is that I will view this, right? I will now make connection to entanglement, and I will view this as a temporal wave function, if you wish, or temporal state on the of the temporal spin chain. Right. So this would be a fictitious wave function, and I will ask about its entanglement properties. Yeah.
Sorry, maybe it's a question, but when I do the tensor network in the same direction, the bond dimension, if I apply u over and over, the bond dimension will grow. So how are you slicing? Like, how do you get that slice before you do whatever you're going to do next?
Well, we will get to that.
Okay.
I think, yeah.
Okay.
That's the core of it. So that's exactly, the question I will ask now. Right. Once I take this viewpoint that this is a temporal wave function, this is an object that gives me minimal complexity for computing dynamics of local observables. And this can be smaller than the full wave function complexity. Right? And the key to that is understanding how temporal entanglement, what is the structure, and how it scales with evolution time. And if we find that this temporal entanglement is so-called area law, so entanglement stays constant or it grows logarithmically with time, then we're in business and we can come up with tensor network schemes to approximate this function. And that's exactly what we'll do for a number of very different physical cases. And the first nice and simple surprise in a way is that this model that I defined, it's a simple looking model, but it's quite rich. So in particular, for non-zero values of all three parameters, it is thermalizing, right? It is quantum chaotic, but once you take this influence functional, or since we are working with discrete time influence matrix point of view, turns out that there is a point, right, for a particular choice of parameters G and J, where you can find the influence functional exactly, even though the model itself is chaotic, so spatial entanglement will be very high. And at this special point, so you can verify that the influence functional has an extremely simple form. Essentially, it completely dephases all the quantum interference contributions, right? So it has a form of a product of delta functions over the configurations of the forward and backward contour. And therefore, also from the point of view of entanglement, actually it has no entanglement at all, right? It's a perfectly Markovian, it's a many-body system which acts as a perfectly Markovian band, even though the model is chaotic, right? So this gives you a nice hint that this formulation is useful, and a difficult problem of chaotic dynamics with a lot of spatial entanglement can actually become pretty easy in this temporal formulation. Now to other exact solutions, right? So another class of problems where we can compute the influence functional and analyze its entanglement properties are integrable models. So in particular, using again the same model as an example, if I turn off the Z field, this becomes solvable by mapping onto free fermions. Right? It's a nice model, by itself, which has edge modes and things like that, but I will not go into that today. And its influence matrix can be computed using essentially Grassmann path integrals, and then what you find, it has a form of a BCS-like wave function on this temporal contour. What is important is that the pairing function is sufficiently local, right, that you can actually prove that you can view influence matrix as a ground state of some fictitious sufficiently local Hamiltonian, and therefore it would have areal entanglement. So you can prove it has areal entanglement, and here is an illustration, numerical illustration, how little entanglement there is. So this is quite a general fact. Actually, non-interacting particles give you low temporal entanglement, right? And we can prove this area law for any non-zero temperature. At zero temperature, you acquire log time correction, but this is still not a whole lot of entanglement. A more interesting example is discretized X-exist chain, which is interacting but integrable by beta ansatz. In this case, there are also some exact solutions that we found, and more generally, numerically, you find that temporal entanglement in this case scales logarithmically with time. So this is, a general property. Whenever you have ballistic quasi-particles, temporal entanglement is low. And this is because your subsystem can interact with a given quasi-particle only once, right? Because then quasi-particle flies away and doesn't come back. And this is a nice fact, but it has actually quite powerful implications for, in particular, quantum impurity models. So let me skim through this part. So for generic interacting systems, we have to, so we don't have, of course, exact solutions, right? So we have to come up with tensor network algorithms, and indeed there are various schemes that we've explored, and conclusion is that there are many regimes when your system is thermalizing, or also many body localized, right? Where this is a good, right? Gives you a good method to study thermalization, transport, in interacting spin chains. But let me actually not focus on this too much today. And instead tell you a little bit about applying what we've learned about temporal entanglement of non-interacting quasi-particles, right, to quantum impurity models. Because these models are exactly like that. So here your environment, right, the way these models work, you have an interacting impurity. For example, there could be a few orbitals and covered interactions, and then you have reservoirs which are made of non-interacting quasi-particles. And therefore, that's exactly the situation, right, where our results apply. So we can, first of all, find the influence functionals of these reservoirs exactly, right? They would be Gaussian, just like this BCX wave function I mentioned. And then there is an algorithm, right? We can essentially adapt Fishman-White algorithm made for spatial Gaussian harmonic wave functions to this situation, and then represent this as each influence functional as a matrix product state. And once that is done, right, this is efficient, and we can compute impurity observables. And what is important is that results on temporal entanglement give you guarantees of efficiency, right? Which is, for example, if you're doing quantum Monte Carlo, that's a lot harder. So, and as I mentioned, if we have, right, the most interesting case of low temperatures, in this case, temporal entanglement grows a little bit faster, logarithmically in time. So, but still, right, this is good enough to have polynomial complexity guarantees. And this tells us that actually, computationally, most of these non-equilibrium impurity models, right, and they, of course, they've been at the center of research in quantum transport and also in DMFT for quite some time. Actually, they can be efficiently solved. Now, there is often a gap between efficiently solved asymptotically and actually solved with current capabilities. But so we went ahead and implemented this algorithms based on these ideas, and actually turns out that off the bat you can get performance which is quite comparable, for example, with pretty sophisticated Monte Carlo schemes. So here I'm showing just as an example a quench of the single orbital Anderson model, right? And you can see the slow dynamics of slow spin dynamics, which is essentially indicative of the formation of quantum singlet. And this also allows you to model non-equilibrium currents, right? So for example, here we are studying, sorry, something happened with equality. We are studying current through the Anderson impurity model with essentially quenching the voltage, right, to some finite value and seeing how the current settles this. Based on that, so we also tried an imaginary time impurity solver together with the Flatiron team. So let me maybe skip that, but the bottom line here is that the scaling looks pretty optimistic, but still we need to improve further to try to attack some of the more complicated models. And instead, so let me spend the remaining, I guess, 7 minutes before questions, jumping to the experiment, right? Because ultimately, everything I told you up to this point was actually boiling down to a simple idea: how many qubits do I need to emulate some many-body path, right? And what I told you that actually, if you're just looking at a subsystem, right, you can emulate any bus of non-interacting fermions or interacting with particles with using just a small number, right? Very small number of effective degrees of freedom. That also, let me make a comment. I didn't, don't have to talk about it, but that also holds for some thermalizing systems, right? Because thermalizing systems are exactly the ones which have, some finite thermalization time, so there isn't a whole lot of memory and non-Markovianity if you're looking at a subsystem. But that story is also interesting. Ask me if you're curious about that. But now I can also turn it around and say, well, if I can emulate a bath using relatively few qubits, I can also go and try to do it in the experiment, right? And try to emulate, for example, a bath which would cool my many-body system, running evolution of just a few auxiliary qubits. And that's exactly what we tried, right? And so this here the system is Google superconducting quantum processor, right? So this is let's say around 70 transmon qubits with tunable couplings, right, arranged in square geometry. And here you can apply any single and two qubit operation. And okay, this is exactly right. This is an what's the next generation of the device which was used in the 2019 quantum supremacy experiment. There, the goal was to create a very entangled wave function as quickly as possible, right? Applying essentially random gates. So, but now what we want to do is actually not what one does in, I would say, majority of quantum simulation experiments where you run some unitary evolution before noise that you don't control completely kills features that you're looking for, right? So instead, actually, let's try to use dissipation to our advantage, right? So of course, there would always be uncontrolled decay and phasing of your qubits, but also what we can do, right? We can engineer some extra dissipation on top of that, and this is, it's been appreciated that engineering dissipation gives you a way to create entangled steady many-body states, right? And you can do quantum computation. There has been, a number of proposals on preparing many-body states for frustration-free Hamiltonians, where you can cook up dissipators which would locally decay to the ground state. So now we wanted to explore something different. So we wanted to study Hamiltonians which are generic and not frustration-free. And really the intuition was that we want to use the notion of quasi-particles and use auxiliary qubits in such a way that they would remove quasi-particles from the system. So the idea is that we would couple auxiliary qubits to the system if our protocol is at the right uses auxiliary qubits at the right energy for the right time, right, with the right coupling, quasi-particles would be gradually removed, and then we would reset the auxiliaries and just repeat this over and over again until we end up in the ground state or close to the ground state. There are several advantages to this strategy. So first of all, you actually do not need to know a priori what your ground state looks like. Right? You need to have some idea of what quasi-particles look like, of their energies rather. And as you will see, this method is actually effective across phase transitions, and we have used it to engineer entangled states in 1 dimension and 2 dimensions. And another nice feature that I will highlight is that steady states can be purified efficiently, and I will show an example of it. Yeah.
Does excitation have to be in the C basis necessarily?
No.
It's a many-body state excitation, something not logical.
No. Yeah. So I guess you're asking what should be the coupling operator, right? That's indeed important, but the exact form of the coupling is not so important. But you're right that you want to have a sufficiently good overlap with the creation annihilation operator of your quasi-particle. But that's right. And here is, just to give you a flavor of this first experiment we did. So first we just looked again back at this simple model, which is a transverse field Ising model, which has two phases, right? Antiferromagnetic and paramagnetic, with critical points separating them. And this is this is a model where in the previous work we imaged, so this is an experimental image of the quasi-particle spectrum and how there is this pi Majorana mode which then splits at the phase transition. So without, so, and here is the protocol. So essentially we are using some auxiliary qubits with just Z gates, right? And the angle of the Z gate is tunable. So that plays the role of the energy or quasi-energy of your ancillas. And then we apply 2-qubit entangling gate. So in this case it was I-swap with some angle, coupling the ancillas and system qubits, and then running a few cycles. Then we do a reset of all the auxiliaries, right, and go on. And turns out that this protocol actually is sufficiently efficient that it can bring you relatively close to the ground state. And so here is the result. So on the left, so once we do that and system reaches a steady state, we can go and image steady state with particle populations. So that requires measuring fermionic correlators, essentially, right, of the form C dagger on side I, C on side J. So in the spin language, these are long products of Pauli operators. So you can do all that, and then back out the quasi-particle population. So here, here, x-axis gives you value, right? Value of G over J, so where you are in the phase diagram, and then y-axis is the quasi-particle energy, and the color is the quasi-particle population. So what you see quite generally here is that this protocol is good at removing high-energy quasi-particles. There is still some quasi-particle left at lower energies. This happens because this cooling protocol is not perfectly efficient, right? But that has advantage of being fast, relatively fast. So it's not bad at battling with the noise. Right? Ultimately, what limits the cooling is uncontrolled noise you have in the system. And another nice property is that actually, in this cooling approach, you got your steady state has some population of quasi-particles, but it can be purified efficiently. Right? So in other words, if you look at the steady state correlation matrix and you find its eigenorbitals are very close to your true quasi-particle orbitals. And here's a demonstration of that. After we do this post-processing, right, and we just declare, so what we do, we find the eigenorbitals and then declare if the population was below 1/2, we declare it to be 0, and if it was above 1/2, we declare it to be 1. And what you end up with actually is very good fidelities, which are, let's say, above 90% for a system of about 20 qubits. And from there, you can, for example, you can nicely reproduce the critical correlations at the phase transition point. So another feature that I will not have time to discuss is that we believe that dissipative state preparation is asymptotically more scalable than variational unitary algorithms. Right, so that's another motivation for studying them. Now, this is a slide before last one, and we still have maybe a minute for questions. So then we also went and tried it in 2 dimensions, and so in here you can also, again, this is for field Ising. So this protocol produces relatively long range antiferromagnetic correlations. Right, so this tells us that also in 2 dimensions, yeah.
So it's related to Eugene's question, not only the form, but also the frequency of this band matters. You're using like a narrow bandwidth band. So how can I convince myself that they can thermalize? Meaning that you're extracting energy at a specific energy.
Yes and no. That's indeed important, right? But you're also resetting, right? So actually, that broadens your bar. But this matters for how quickly you're pulling different nodes. You're right.
I'm always extracting that omega, but you're saying that the rate of it is not exist.
Yes, right. So this protocol is not the optimal. There are better ones, which we know. So let's discuss it. But let me conclude here. So I think the main message, right? The main message I wanted to convey is that actually there are many examples of quantum path that can be emulated or approximated just using a few qubits, right? And this gives rise to both a family of new efficient methods based on temporal entanglement and with applications to many-body dynamics and quantum impurity models, and also ideas for using engineered dissipation for correlated many-body states. So let me just thank the collaborators. So on the more temporal entanglement side, Alessio Lerosa, who was in Geneva, now at Oxford, and PhD students Mikhail and Julian have really developed this set of ideas. On the experimental side, I think Shao, right, was the experimental lead on this work. Vadim, all of the team. Thanks a lot.